Hello everyone, my name is Umayma Ben Hatta. I'm a PhD student in the Sultan Moulay Slimane University in Morocco. My research interests design and miniaturization of antenna for wireless application, and my presentation today is design and simulation of dipole antenna using the method of moments. My presentation plan is organized as follows. First, introduction. After that, we will present Hallen's and Pocklington's integral equations, and before present the simulation results and discussion, we will show the method of moment as solution of Hallen's and Pocklington's integral equations, and finally a conclusion. An antenna is a device for receiving or radiating radio waves between given devices and free space, and it is used in several applications such as radio communication, WLAN applications, aeronautics communications, mobile communication, radar, vehicle communication, and so on. A dipole antenna is the simplest class of radio antenna. It consists of two conductive elements such as metal wires, which are usually symmetrical, with a small space between the two conductors where the feed line is connected. Several critical parameters are affecting the antenna performances, such as current distribution, field patterns, resonance frequency, impedance, and gain. And these characteristics can be determined by solving the electric field integral equation of the antenna. Many numerical techniques have been used for antenna design because analytical techniques have difficulty for complex structure. The most used techniques are the method of moment, the finite element method, the finite integration technique, and the finite difference time domain. And the method of moment is a powerful numerical technique to solve electromagnetic integral equations, and it will be applied to Hallen's and Pocklington's integral equations commonly used for dipole antenna design. The aim of this work is to present a fast and efficient algorithm for solving Pocklington's and Hallen's integral equations. This algorithm employs the method of moment to determine the antenna characteristics in terms of current distribution, E-field, and impulse impedance. And in order to validate this algorithm, two types of dipole antenna, which are half-wave antenna and full-wave antenna operating at 115 MHz, have been analyzed. Now we will present Hallen's and Pocklington's integral equations. Consider a dipole antenna as shown in figure 2 of length L and radius A, collinear with the axis OZ. Where there is no dependence of the angle phi, we can write the potential of the corresponding magnetic vector EV in cylindrical coordinates by the expression presented in equation number 2, where R is presented in equation number 3, and if we assume that the radius A is very small than the length L, we obtain R is equal to square Z1Z prime 2 plus O2. And with the same approximation, the potential of the corresponding magnetic vector becomes presented by equation number 5. And the expression of the radiated fire is given by equation number 6. And by enforcing the boundary condition of the tangential electric field in zero at the surface of the wire, we obtain that the tangential electric field is equal to minus the radiated field. And substituting equation number 5 in equation number 7, we obtain the Han's integral equation presented by the equation number 8. And if we move the differential operator under the integral sign, we get the Pocahontas integral equation defined by equation number 9. Now we will present the method of moment as solutions of Han's and Pocahontas integral equations. The method of moment is a numerical technique which transforms an integral differential equation into a matrix system linear of equations. The solution starts by dividing the dipole antenna into small segments and model the current distribution in each element by a geometrical function such as rectangular, triangular, cylindrical function, and the boundary condition reduce the problem into a matrix equation, and the solution of this equation yields the impedance matrix. First, we will start by solving Han's integral equation, which is an homogeneous scalar Helmholtz equation for easy, which we can solve by the green function method. The particle solution to the homogeneous equation is presented by equation number 10, and expanding the left side of the equation number 10 using n-weighted subdomain basis function, yielding and tested by n function fn, give the equation number 11. For writing this in matrix form, gives us Vmn multiplied by A is equal to D1 multiplied S plus B. And to obtain the solution of this vector, we must determine the constant D1, which we can be done by enforcing the boundary condition at the ends of the wire, and D1 is given by equation number 13. And by using the symmetric Han's equation with path basis function and point matching, the impedance matrix becomes Zn is defined by equation number 14, and the right side of vector elements are S is equal to cosinus chi Zn, and B is equal to sinus k Zn. Now we move to the solution of Pocahontas integral equation. First, we develop the current in a set of basic functions as presented in equation number 15, and substituting the current in the Pocahontas equation, we obtain equation number 17. Writing this in matrix form, we obtain that Vmn multiply An is equal to Gn, and using path basis function for the current and point matching for testing, we obtain the impedance matrix presented by equation number 9. For the simulation, we based in the following algorithm. First, we define the simulation parameter, frequency, the length of the dipole antenna, the radius, the number of subdivisions. After that, we build the impedance matrix by equation number 14 for Han's integral equation, and by equation 19 for Pocahontas integral equation. After that, we compute the admittance matrix. Then we compute the source voltage. After that, we compute the current distribution by equation number 12 for Hallen integral equation and by equation 19 for Pocklington equation. After that, we compute the input impedance and then we compute the pattern by equation number 11 for Hallen equation and equation 16 for Pocklington equation. The suggested algorithm is verified by comparing its results obtained by MATLAB code with a CAD solver result. Figure 4 presents the results for current distribution acquired by Hallen and Pocklington integral equations solved by MATLAB's code using the method of moments, together with the outcomes determined by CAD. It can see that the current distribution that appears along the length of the designed dipole antennas falls at 0 at the end and then varies sinusoidally. The results obtained are in excellent agreement with each other. And for the simulated O-field, the radiation pattern of the dipole antenna is presented in figure 5, and it is noted from the figure that the O-field radiation pattern for the half-wave and full-wave dipole antenna is directional at the resonance frequency and according to the same figure, and it's clear that the simulation results obtained by MATLAB's code and CAD code are particularly identical, and the maximum O-field managed for the half-wave antenna at the resonance frequency is about 0.696 volts and about 0.727 volts for the full-wave antenna. And the table shows the simulated impulse impedance at the resonance frequency acquired by the different methods, and the results are almost similar even if we remark some small difference. And in terms of conclusion, in this present work we applied the method of moments to solve Hallen's and Pocklington's integral equation with pulse function, and MATLAB's code is used to determine the current distribution, the O-field radiation pattern, and the input impedance. The results obtained by different methods are in excellent agreement with each other and validated by CAD code, the best known solver based on the method of moments. And thank you for your attention.